Hello everyone, my name is Pablo Jimeno from the University of Zaragoza, and I am here today to present our paper entitled Convolutional Recurrent Neural Networks for Speech Activity Detection in Naturalistic Audio from Apollo Missions. I would like to start with a brief outline of today's presentation. First, I will comment on the speech activity detection task, giving a brief introduction to it, and commenting a little bit on the current state of the art. Secondly, I will introduce the Fearless Steps challenge, that this is the main context for this paper, and that is focused on the use of different audio from Apollo space missions. Thirdly, I will present our proposed SAD system, which is using its main element convolutional recurrent neural networks. Then I will describe our experimental setup, presenting our data for training and evaluation, and briefly commenting on the metrics for the evaluation. Finally, I will describe our results for the task and will comment on the ranking in the final classification. So, speech activity detection is a task that aims to correctly identify those audio segments containing speech. This is an auxiliary task that works as a support block for many other speech-related tasks, such as speech or speaker recognition, for example. An accurate speech activity detection can help improving the accuracy of those speech-related tasks. So far, a large number of approaches have been proposed for the SAD task. For example, if we focus on those that are unsupervised, we can see energy-based systems or systems that are based on the use of long-term spectral divergency, for example. If we focus on the statistical model, we can see GMM approaches or other approaches that are based on the use of specific acoustic filters, for example. Recently, the use of deep learning is very popular, mainly being the current state of the art for this task. We've seen a lot of approaches based on the use of recurrent neural networks with LSTM layers, for example. And more recently, we've seen the convolutional and recurrent neural networks combined in what is called convolutional recurrent neural networks. I will now talk about the Fearless Step Challenge. This series of challenges have been proposed over the last few years in order to deal with audio coming from Apollo space missions. This is a really challenging domain with a strong degradation and several transmission noises present in the audio. So far, different speech processing tasks have been proposed for this challenge, as for example, speaker diarization or automatic speech recognition. In this paper, we introduce VivoLab submission to the speech activity detection task. The second phase of the Fearless Step Challenge was presented in the year 2020 with a change in the focus of the challenge. The focus now in the year 2020 was set on the development of supervised approaches. This was supported also by the release of around 80 hours of human label data. Well, with this new data available, we propose a deep learning solution for this task that is based on the use of convolutional recurrent neural networks as the main element in our system. Okay, now I will explain the neural architecture that we have explored for this paper. Namely, we've been working with CRNN architectures that use both 1D and 2D convolutional filters. As you can see here in these figures, System A is based on the use of a convolutional 2D block composed by a convolutional 2D layer, a batch normalization layer, a ReLU activation, and a frequency pooling mechanism. The B system is very similar to the first one, but instead of using 2D convolution, it's using a 1D convolution as the main element. We also experiment with 3 different kind of 1D convolutions. We experimented with dilation and with group convolution for this system. Furthermore, we introduce a novel architecture that is based on the fusion in an intermediate feature space of both 1D and 2D filters. Also, you can see here in this figure that all our systems share a common element, that is the RNN block, that is composed by 3 bidirectional LSTM layers and a final linear layer. Okay, now I will comment on the fusion implementation for our new proposed architecture. We implemented this fusion mechanism in 3 different ways. We experimented with 3 of them. First, we made the fusion by means of a bilinear layer that combines both the 1D and 2D filters information. Secondly, we use the sum of both feature maps, the 1D and 2D feature maps. And finally, we use the concatenation of the information coming from the 1D and the 2D filters. We will evaluate the 3 of them in our results. Concerning feature extractions, we've been using a traditional perceptual features. Namely, we use 64 log MEL energies concatenated with the log energy of the frame. These features are computed every 10 milliseconds with a 25 millisecond Hamming window. Finally, mean and variance normalization is applied at file level in order to get a zero mean and unit variance feature input. All the systems that we present in this paper share the same set of features. Concerning the data we've been using in our paper, the fearless step challenge follows open training condition. This means that any data available for the participants can be used for training the system. Yet our system is only based on the data that is provided by the organization. This was done in 3 different partitions. The trained partition is made of around 62 hours of audio. We reserve 10% of this data for training validation, and we use the rest for training our neural networks. Concerning the development partition, this is made of around 15 hours of audio. In our system, we use this set to tune the optimal threshold for the SAD system. We also report our results on this development set. Finally, the evaluation set is made of around 20 hours of audio and is the one that is used to rank the participant in the final leaderboard. We will also report the results of our system in this subset. Concerning the evaluation metric used for this challenge, this is the detection cost function, DCF. And as you can see here in the formula, for this challenge, false negative errors are considered more important than false positive errors. We will take this into account when finding the optimal threshold for our system. Okay, in the following slides, I will be briefly commenting our results. If you want to see a more in-depth explanation of them, you can check the full paper for a more clarifying explanation. You can see here first both the organization and our recurrent neural network baseline. And then the systems are separated in 3 big groups, those using 2D convolutional filters, those using 1D convolutional filters, and those using our fusion architectures. We can see immediately that all our proposed system largely outperformed the organization baseline. But we can also see that the convolutional recurrent neural network in all variations outperform the bidirectional LSTM baseline. If we focus on the three different groups, we can see that the best performance is obtained by the fusion architecture, suggesting that this fusion is beneficial for the SAD system. We can also see that the 2D filters obtain a better performance than the 1D filters by themselves. And if we focus on those using 1D convolutions, it is interesting to mention that the 1D system using group convolution achieves the same performance as the one using the 1D convolutions with a significantly lower number of parameters. Okay, here in this figure you can see a qualitative visualization of the speech score for a single file of the development subset. As you can see here, our system is accurately capturing the variation on the ground truth SAD. It also must be noted that no smoothing or post-processing technique are applied on the output of the system. This suggests that the output of the bidirectional LSTM layer is smooth enough to be used by itself. Okay, finally, this table summarizes our best submissions for the challenge. As you can see here on the eval subset, competitive results were obtained with a large outperform of the baseline provided by the organization. As you can see here, our best submission that is based on the use of the fusion architecture achieved an eval DCF of 1.78. This number ranked 7th among the 28 submissions to the SAD task in the challenge, resulting in our team ranking 4th among the 7 participant teams in the challenge. So let's finish with some conclusions for this paper. We introduce VivoLab submission to the SAD task of the Fearless Step Challenge that is aimed at dealing with audio from Apollo space missions. For our submissions, we explore different CRNN models using both 1D and 2D filters in the convolutional layers. Furthermore, a new architecture is proposed fusing both kind of filters in an intermediate feature space. Our experimental results suggest that this fusion is beneficial for the SAD system, yielding the best results for all our submissions. Finally, competitive results were obtained with a ranking of 4th among the 7 participant teams in the challenge. So that's all. Thank you very much for listening. If you want more information, you can read the full paper. Thank you.